I'm going to show you the virtual work principle for beam structure. Using this cantilever beam as an example, I apply an external force of F and the beam will deform. I want to find the deformations of the beam at any location. So as you know that the external force is going to create internal force inside the beam. And we say that the strain energy of the beam saved inside the beam will be predominantly due to the bending moment. So let me use a small elements as an example to illustrate to you how much energy has been stored inside that small element. So this small element is dx, and the bending moment applied on both sides is m. This small element is going to deform due to this bending moment. And such a deformation is classified by d theta. So according to moment curvature equations, d theta is equal to m over ei times dx. Hence, the strain energy stored inside this small element is equal to 1/2 m times d theta. So if you integrate for the whole beam, then the strain energy saved inside this beam is equal to 1/2 integrations m times d theta, which is equal to m over ei dx, according to moment curvature equation. So here is a strain energy expression for the beam. And here is the work done by this external force. 1/2 F times the corresponding deformations at the loading position. And here is the work and energy equation. Now I want to perturb the structure away from its equilibrium by holding the deformation constant, but imagines that I have an additional imaginary force applied, delta F. Such an imaginary force is going to cause additional bending moment inside the structure. This is imaginary bending moment developed inside the beam due to the imaginary force, delta F. So according to virtual work principles, this virtual work is going to be equal to virtual strain energies. So virtual work is equal to delta W equal to delta F times delta F. While virtual strain energy is virtual bending moment times d theta, which is equal to m over ei dx. So for the whole beam will be integrations, delta m times m over ei dx. And virtual work principle tells us that the virtual work should be equal to the virtual strain energies. So if you equate these two, then here is the virtual work principle for a beam structure, which shows you that delta F times delta F is equal to integrations delta m times m over ei dx. Let me summarize the virtual work principle for beam structures in this slide. So this is the cantilever structures under a set of external loading, and I wish to find deformations at the particular locations of the structure. And here is the virtual work principle we just derived for a beam structure. So I highlighted in yellows are corresponding to those terms that coming from actual situations. So this is the internal bending moment due to the external force, actual external force. And this is the deformations of the structures that we wish to find. So you need to assume that there's a virtual force along the same directions of the deformations that you're looking for. That's called delta F. And such a virtual force is going to create additional virtual bending moment. So this virtual bending moment is going to show up on the right-hand side of the equation. So here is the virtual force that you assume, and here is the virtual internal bending moment induced due to this virtual force. So you just have to assume a virtual force there, calculate the internal virtual bending moment, and here is the actual bending moment that you can determine from the actual loading conditions. Again, the only unknown remains is the deformation, delta F. So you can use the similar concept to calculate rotation angle as well. For instance, I want to find rotation angle at the free end, theta A. So rotation angle theta A is due to the set of external loading. So what I can do is I can assume that a virtual bending moment is applied at that particular locations. This is called delta MA. Such a virtual bending moment is going to again create additional bending moment inside the beam, virtual bending moment inside the beam. So as a result, you can use these equations to calculate rotation angle, theta A. So you assume virtual bending moment, MA, and that assumed bending moment is going to cause additional virtual internal bending moment, delta M. And again, this M here is the actual bending moment caused by the actual force. So the only unknown in these equations is theta A. To extend this virtual work principle to frame structures, you can consider the frame structure as a combinations of truss structure and beam structure. So you can follow the same principle, delta W equal to delta U. So the virtual work done by the external force remains the same. On the right-hand side, the strain energy is going to be consisting of the contribution from axial force and bending moment. So quite normally, the contributions of axial force into the strain energy is normally very, very small in compared to the strain energy contributing from the bending moment. So in practice, we usually ignore the contributions of the axial force in the calculations.